Mode seeking meets mean seeking for fast, long video generation. If you're an AI researcher or an ML engineer trying to scale diffusion models from a few seconds to minute-long generations, you already know the core bottleneck of this entire field. Short video data is incredibly abundant and high fidelity, but coherent long video data is, well, it's essentially a scarce commodity.
Right, and the fatal flaw in current scaling methods is treating temporal extrapolation exactly like spatial interpolation. We've seen that upscaling resolution works beautifully, but blindly extrapolating time just leads to blurry, low-fidelity long videos.
Which brings us to this paper's highly elegant solution, the Decoupled Diffusion Transformer, or DDT. It splits the learning process entirely in half. You have a global flow matching head that uses supervised learning on that scarce long video data to capture minute scale narrative structure. That represents the mean-seeking part of the equation.
And simultaneously, a local distribution matching head aligns sliding windows of the generated video to a frozen, expert, short video teacher model. It uses a reverse KL divergence to capture high-fidelity dynamics, which is your mode-seeking part.
The ultimate takeaway here, at inference time, you drop the flow matching head entirely. You only use the few-step distribution matching head, which unlocks fast, minute-scale video generation that maintains incredibly sharp local dynamics while still keeping perfectly coherent long-range structures.
It is a brilliantly practical approach to a problem that has been frustrating the video generation community for the last year. You get the structural integrity of a long context model without sacrificing the crisp, dynamic realism of a heavily optimized short video model.
Okay, let's unpack this, because to really appreciate the architecture here, especially for those of you following along with our AI paper podcasts, we need to look at why the current default approach is causing so much frustration. Think about how modern video generation typically scales right now. You're an ML engineer, you have a massive compute budget on the line, and you're probably relying on what the industry calls mixed-length SFT, or supervised fine-tuning.
Yeah, you take your model and you throw it into a massive data soup of varying video lengths. Some 5 seconds, some 20 seconds, maybe a few 60-second clips if you can actually find them.
The implicit hope there is that the network will just
smoothly interpolate across those different temporal horizons. We've seen this work in image generation, so the assumption was that video would behave similarly. But the paper demonstrates clearly why that assumption is fundamentally broken. They use a fantastic visual analogy comparing image resolution interpolation to video temporal extrapolation.
like the kitten picture.
Exactly. You take an image of a kitten and upscale it from 256 by 256 to 1024 by 1024. It works beautifully. The reason it works is because the image patches share the exact same underlying statistical distribution. A patch of orange fur is still a patch of orange fur, just sampled at a higher frequency. You are interpolating between known data points.
But time doesn't work like a spatial grid.
Not at all. Scaling a 5-second video to a 60-second video is not interpolation. It is pure extrapolation. You aren't just adding intermediate frames between a start and an end point. You are extending the horizon into the absolute unknown. To do that successfully, the model has to introduce entirely new events, establish complex causal chains, and sustain a narrative structure that simply does not exist in a 5-second training window.
If a glass strikes at second 3, it has to shatter at second 4.
And it cannot unshatter at second 40. That requires a completely different type of reasoning.
Right. And when you force a model to train on this mixed duration data soup, you see a very specific and frankly painful symptom. You spend all this compute, you wait weeks for the run to finish, and the resulting long video loses the incredibly sharp local dynamics that your expert short video teacher originally possessed. The outputs become noticeably softer, blurrier, and just feel less alive.
By training jointly on a mix of scarce long videos and abundant short videos with a standard flow matching objective, the network is forced into a corner. It has to relearn its high-fidelity short video priors in a compute-constrained regime. You are asking a single network capacity to satisfy two radically different distributions.
So it just compromises.
The inevitable result is a compromise smoothed over average. It's hedging its bets across the time domain.
So the paper proposes the decoupled diffusion transformer to fix this, but how does it actually plug into the existing architecture? Are we operating directly in pixel space here?
No, we're operating natively in the latent space of a video VAE, utilizing a rectified flow parameterization. The foundation of this architecture relies on a shared spatiotemporal feature encoder. Let's call it EFI. This encoder takes in your noisy long video latent, the current diffusion time step, and your text conditioning. It processes all of that using full attention to produce a unified, deeply contextualized representation.
Attaching two separate decoder heads to a single encoder sounds computationally expensive and, frankly, like it would cause massive gradient interference. How do they actually resolve that tension?
That tension is exactly what destroys standard models. If you try to naively apply a long video structural loss and a short video high-fidelity loss to a single velocity predictor, the gradients literally fight each other in the network. The long video objective wants to average things out when it's uncertain, to keep the overall structure safe.
And the short video objective wants to commit hard to a specific sharp reality.
Exactly. By decoupling them into separate, lightweight transformer decoder heads, the shared encoder learns a robust foundational representation. But the spiralized heads handle their specific objectives without clashing in the final output layers.
Let's look at how these two heads operate. Starting with head 1, the flow matching head. This is the mean-seeking component.
This head acts as your long context anchor. It is trained using supervised flow matching standard SFT on the ground truth full-length videos. So it's looking at the entire minute scale sequence from start to finish.
SFT is inherently mean-seeking. What does that actually look like in practice for the model?
When a model is trained with an L2 loss on diffusion noise over a long, highly variable sequence, it naturally tends to predict the statistical mean of all possible outcomes whenever it faces ambiguity. Imagine you're writing a vague essay to cover all bases on a test because you aren't sure of the exact answer.
That's a great way to put it.
That's what the model is doing visually. For learning global trajectories, ensuring a character stays the same person over 45 seconds, and maintaining narrative structure from a limited data set, this behavior is fantastic. It keeps the video from structurally falling apart.
But averaging under ambiguity equals visual blurriness when it comes to the details.
It is terrible for generating fine textures, like the weave of a fabric or the crisp splash of water. It smooths everything out to play it safe.
Here's where it gets really interesting. Head 2 is the distribution matching, or DM, head. This is the mode-seeking component, and it abandons the full sequence entirely to operate on a local sliding window approach.
While the flow matching head stares at the whole long sequence, the DM head evaluates contiguous bite-sized segments, think 5-second windows, and it crops these directly from the student model's own long-generated rollouts.
So it's an on-policy evaluation. It's looking at what the student is actively generating in real time, rather than comparing to a static data set.
It evaluates these generated windows using a mode-seeking reverse KL divergence. The goal is to match the marginal distribution of these generated windows to an expert, frozen short video teacher model, like a highly optimized, pre-trained 5-second DIT model.
For the engineers listening, calculating a reverse KL divergence directly in this high-dimensional space is intractable. You can't just run a standard loss function on it.
You have to use gradient surrogates. The authors employ distribution matching distillation, or DMD, and variational score distillation, VSD. Essentially, the gradient of the reverse KL between the student and the teacher can be expressed by the difference in their velocity scores on noisy states. You train a fake score estimator on the student's window predictions, and you compare that against the teacher's velocity query on that same noisy window.
Let's ground that math for a second. It pushes the student to stop hedging its bets. Instead of writing that vague essay we talked about, the reverse KL forces the student to pick a single definitive answer. It seeks out the sharp, high-density modes of the teacher's distribution, committing to a crisp, high-fidelity reality for every single 5-second window.
That sums up the intuition perfectly. The local windows are forced to look as sharp as the teacher's output, while the shared encoder ensures those windows string together logically.
Okay, that sounds great in theory, but cropping a 5-second window out of the middle of a continuous latent space generation sounds like a nightmare for the teacher model. Doesn't that completely break the expected input semantics?
Oh, it's a massive hurdle, and how they solve it is a brilliant piece of engineering. Remember, we are working in the latent space of a video VAE.
Yeah.
When you train a short video teacher model, it expects the very first frame of its sequence to be a pristine image latent. That's how these models are initialized.
Right.
But when you crop a window from the middle of a 60-second generated video, the first frame of that cropped window is a video latent. It's deeply embedded in the temporal sequence.
If you feed that raw middle crop to the frozen teacher, I imagine the teacher completely fails because the input is out of distribution.
It throws garbage gradients because the semantics don't match. To fix this, for any sliding window that starts after the 0th frame, the researchers literally synthesize a fake first frame. They decode the latent prefix, the part of the video generated right before the window starts, using the frozen VAE. They extract the absolute last RGB pixel frame of that prefix. Then, they re-encode that single frame from scratch into a pure image latent and prepend it to the sliding window before computing the DMD loss.
They synthesize a pristine image latent mid-generation just so the teacher model can properly digest the sequence. That is a highly clever hack to make sliding window distillation work on continuous latents. But doesn't running the VAE decoder and encoder in the middle of a training loop absolutely torch your compute budget?
It would, but they implement a stop gradient. They mask that reconstructed latent out so you do not backpropagate through the VAE, you only use it as a clean conditioning frame for the teacher. That keeps the whole process compute efficient while providing accurate gradients.
Which perfectly sets us up for the inference phase. After all this complex training with two heads, when it's actually time to generate a video for a user, you throw away the flow matching head entirely.
You literally discard it. It has served its entire purpose during the training phase.
You only use the distribution matching head, the one supervised exclusively on 5-second sliding windows.
Yeah.
But it can directly generate a full 60-second video end-to-end bidirectionally. Why does that work if it only ever saw 5 seconds at a time?
Because both heads were constantly updating that shared spatiotemporal feature encoder during training. By the end of the run, the shared encoder has been fully shaped by the global, minute-scale data from the flow matching head. The macrostructural map is permanently baked into the encoder's representations. The DM head simply reads those structurally sound representations and applies its high-fidelity, mode-seeking local priors over top of them.
And because the DM head was trained using DMD, a distillation technique, it functions natively as a few-step sampler. You get fast inference without needing hundreds of diffusion steps. Now, we love a good ablation study on these deep dives. To prove this decoupled architecture is necessary, the authors dismantled it piece by piece. What happens if you remove the dual heads and try to train a single head with both the SFT and DMD losses?
You see massive quality drops across the board. The gradient interference we talked about destroys the model's ability to optimize either objective effectively. It becomes a worse version of both.
And if you keep the architecture but turn off the sliding window DMD entirely?
The model degrades right back to the blurry, SFT-only baseline. It loses all the high-frequency textures because it has no mode-seeking pressure.
Conversely, what if you remove the flow-matching SFT anchor and only use the sliding window teacher alignment?
You get incredibly crisp motion, but zero minute-scale narrative structure. The video looks visually stunning from second to second, but over 30 seconds, the scene morphs incoherently. The main character might turn into a completely different person because the short video teacher is inherently blind to long-range context. Every single piece of this decoupled architecture is load-bearing.
Let's talk about how this stacks up against the current baselines. The researchers tested this on the 2.1 architectures, specifically the 1.3 billion and 14 billion parameter models.
Proving the method scales effectively to frontier-class models, not just toy examples on small data sets.
They tested against some heavy hitters, specifically autoregressive or AR, baseline methods like CosVid, self-forcing, and infinity rope. AR methods have been very popular for extending video length recently.
They have, but they suffer from error accumulation. In an autoregressive rollout, the model generates a chunk, conditions on it, and generates the next chunk. Slight visual artifacts in the early frames compound over dozens of steps. By the time you reach 60 seconds, the video quality is usually degraded into a noisy mess.
Or the model learns to cheat the metrics. You pointed this out in the results regarding infinity rope.
This raises a critical question about how we evaluate long video models. Infinity rope uses sync mechanisms to attach generation to certain frames to force consistency. When you look at its consistency metrics on paper, it scores incredibly high. But watch the actual video. It generates highly static, uneventful content. It games the metric. If the camera doesn't move and the subject barely breathes, of course consistency is high. But its dynamic degree score is terrible. It's the classic ML trap of optimizing a metric at the expense of the human goal.
The qualitative visual proofs in the paper really hammer this home. There's a vivid example of a prompt asking for a pirate walking through a bustling town.
A perfect test case for both long-range consistency and local detail.
If you look at the SFT baselines, the fine textures of the pirate's coat are washed out into a smooth blur, and the viewpoints shift abruptly over time. The teacher-only AR methods manage to keep the coat sharp initially, but the motion eventually collapses or becomes completely static to avoid that error accumulation we just talked about.
But the decoupled method keeps the foreground subject remarkably crisp. The textures of the fabric are retained, and the background tone evolves smoothly without jarring shifts. It is visual proof that mode seeking and mean seeking have successfully merged.
So what does this all mean for you, the listener? If you are building video diffusion models, this paper provides a highly actionable blueprint. You do not need to curate and filter massive, impossibly expensive data sets of highly dynamic minute-long videos to get minute-long generation. You can take the highly refined short video priors you already have, models trained on the abundant 5-second clips from the web, and stretch them into coherent long-form generation. And you can do it with a fast, few-step inference process.
If we connect this to the bigger picture, the implications extend far beyond just making longer stock videos. The authors hint at this heavily in their future work section. Because this decoupled architecture creates a native, bidirectional long-context encoder, you are fundamentally building a persistent history representation.
A memory of the world's state.
A memory that doesn't decay. A persistent history representation has been the absolute holy grail for interactive world models. Right now, models struggle to bridge the gap between passive video generation and interactive AI. If you take this decoupled representation, which already intuitively understands minute scale consistency and high-fidelity physics, and you add action conditioning on top of it, you change the paradigm entirely.
Like a high-fidelity version of Google's Genie model, but one that doesn't hallucinate its own environment away after 10 seconds of gameplay.
Exactly that. Imagine generating a fully playable, minute-scale environment where you can explore a room, turn around, and the objects you saw 30 seconds ago are still perfectly rendered in their exact locations, with crisp textures. By separating the structural memory from the local rendering, this architecture could be the exact foundation needed for true, controllable world simulation. Let that idea simmer as you design your next diffusion architecture. The bridge between video generation and interactive game simulation just got significantly shorter.